All right, welcome everyone to another Wolfram Institute seminar. I'm quite happy to have Vaclav Zatloukal with us today. He is one of my former collaborators and friend, so it's always a pleasure to welcome someone that's familiar to our community. Vaclav's work, well, we met in the context of mostly discussing geometric algebra and sort of foundations of physics and how to understand several formal aspects of classical and quantum mechanics from the point of view of the mathematical structures involved. So we spent some fun times in retreat in the Alps and in the sort of France, the French countryside, trying to figure out questions about how to bring out some of the kind of intuitive physical intuitions or ideas in with mathematical form. So today I think we're going to be exploring something different, and I'm excited to hear about this topic, which I haven't really heard from Vaclav himself. So please, Vaclav, take it away.
Okay, so thank you, Carlos. So today I will talk about spinors and about an approach using 2x2 matrices to discuss space-time spinors and how this representation of spinors relates to more traditional Dirac spinors and how this can be visualized and understood in the realm of geometric algebra. So basically, this would be like the first motivation slide, and say you take a space-time vector v mu, and it's well known that it can be represented by 2x2 Hermitian matrix, capital V, just using the Pauli matrices and the identity for sigma mu, and so you form this linear combination of the Pauli matrices with the coefficients being the components of the 4 vector, and you get a matrix which is Hermitian. And if you look at the Lorentz transformations, so how they act on the 4 vector, this translates in the action on this matrix representation, and this action is like this two-sided action where SR lambda is a spin representation, or more precisely, right-handed spin representation of the Lorentz transformations. I will have more to say about these spin representations, but this is just what holds. And so the idea is, if we somehow take a square root of this matrix V, which is Hermitian, and hence we can look for the square root, then the square root, is M, which I will call the matrix spinor, will transform single-sidedly. So it will transform kind of as a spinor, as a Dirac spinor that one knows. So this for me is like the most direct way to spinors, and this M is what I will call matrix spinors, and I will show that this is just like a different representation of the spinors that one knows from the space-time of the Dirac spinors. So the talk will be as follows. So I will detail this square root of a matrix representation of a 4 vector, because there are some subtleties how to take the square root. Then I will show that the ensuing 2x2 matrix M, how it is equivalent with the Dirac spinors, which is like a 4-component Coulomb vector, and then provide some geometric interpretation once we realize that the matrix spinors are nothing but the matrix representation of spinors that are known in the realm of real Clifford or geometric algebras. So yeah, so let's get on that. So let's take the square root. We have a 4 vector, we have its matrix representation. There are some identities that one can easily derive. So the components V mu can be retrieved from the matrix by this trace. And if one takes the determinant of the matrix representation of a vector, one gets its Minkowski norm. Yeah. And now, so since V is Hermitian, we can diagonalize it with the unitary transformation P. We can easily find the eigenvalues as well, express them in terms of the components of the 4-vector. And now, more conveniently, we'll take out the modules of the eigenvalues and just leave the sign and define the matrix M. And now, depending on the signs that we get in between the M and M dagger, we can have we have to distinguish some cases. So some discussion, and basically the signs of the eigenvalues are reflected in the signs of the determinant and the trace. Yeah, because those are the eigenvalues, and in turn, the determinant and the trace are related to the components of the 4-vector, or to the Minkowski norm. So we can then phrase those 3 cases in terms of like different cases for the space-time vector mu, and it can happen that so say for both eigenvalues being positive, we get a 4-vector which is time-like or light-like. So V mu is greater than 0, and in that case we just have P equals M times M dagger when the signs of the eigenvalues are both positive. Then we can have both negative eigenvalues, and we get this second case. So it's like time-like or light-like, but now the 0 component is negative, so it's past pointing 4-vector. The first case was future pointing 4-vector. And then we can also have space-like 4-vector, and this is the case of determinant being smaller than 0. So, and in that case, the 2 eigenvalues have different signs, and the square root amounts to like sticking the sigma 3 matrix in the middle, where sigma 3 is like 1 minus 1 on the diagonal. So this is the convenient way how to take the square root, and indeed, if V will transform in this 2-sided representation, then M would naturally transform into 1-sided spinor representation. Now, so given any 4-vector, we can always find a spinor M for it. So we can always take the square root in the sense above. And in turn, given any 2x2 complex matrix, that gives rise to a 4-vector, or actually to several 4-vectors that we can imagine. We can either take plus or minus M dagger, or make a space-like 4-vector out of it, M sigma 3M dagger. Now, but this spinor is not unique. Like we can for certain 4-vector, there are many spinors that give rise to the same. And if we modify the matrix M by multiplication by the matrix U, then this preserves V in the case U is unitary for the time-like or light-like case, or for the plus minus M dagger, or for the space-like case if U is from the Lie group U11. In either case, this is the freedom of 4 parameters, 4 real parameters. So the spinor M has more information. It has 8 real parameters, the 4 complex numbers of the 2x2 complex matrix, and the vector has only 4 parameters, and the extra 4 parameters are this freedom. Maybe a nice way to decompose a spinor is just a simple polar decomposition of a matrix. So you just write any matrix as a Hermitian, positive semi-definite matrix times a unitary matrix. And from this decomposition, one can see quite directly that if you form a time-like vector dagger, then only the Hermitian part takes place in the expression for V. So the unitary part is lost in the transition from spinors to vectors. So the spinors somehow is a quantity that somehow possesses more information. I mean, this is nothing new. I'm just talking about matrices where those properties of spinors they have more information than the vectors. It's quite nicely vividly seen. As a note, perhaps a note that if the determinant of M of the matrix spinor is 0, this means that the two coulombs, so they are linearly dependent. Then what we get for the vector V is expression down here. The determinant of M is 0, and hence also the determinant of V is 0. So we are dealing with time-like vectors, and they are determined essentially. The direction is determined by this two-component phi, little phi, which is called twister in Penrose and Rindler. So then one gets to the realm of twisters to represent light-like four vectors, but this is just a special case. Now, how this matrix spinor, so the 2x2 matrices M, how do they relate to like conventional Dirac spinors that one knows from relativistic quantum mechanics or quantum field theory? So just to recall, we have Dirac gamma matrices, and we have various representations of those gamma matrices, 4x4 matrices. For our purposes, it turns out most convenient to use the Weyl or Kyler representation. And so the Dirac spinor is a like Coulomb vector which has 4 complex components. In the Weyl representation, one usually talks about the so-called left-handed component of the spinor and the right-handed component of the spinor. So both of them are like 2-component spinors. And the gamma matrices have this off-diagonal form, which is quite nice, as we will see, where also one denotes by sigma bar, like the Pauli matrices with the opposite sign, and the identity matrix is the same as for sigma mu. So one has just this sign swap in the definition of sigma bar. For the sigma mu bar, one can easily see that the following identity holds. It's also quite useful. So the star will always denote complex conjugation here, not the Hermitian conjugation, just to be sure. Now, the Dirac spinors, well, they transform under Lorentz transformations in the spin representation, which is the spin representation of Lorentz transformation is a 4x4 complex matrix. This S lambda, which in the Weyl representation is block diagonal, because the gammas are off diagonal, so that the spin representation turns out block diagonal, and this is very convenient. So now maybe a bit more about these spin representations. So the two blocks SL lambda and SR lambda, so they are the left-handed spin representation and the right-handed spin representation, and they transform the spinors, the left and right-handed spinors respectively, or left and right-handed part of the Dirac spinor respectively, and they only differ in the sign here in front of the zeta I sigma I. So the parameters phi I, they parameterize spatial rotations, and the zeta i's, they parameterize boosts. and we get this like matrix exponential expression for the spin representation matrices. And due to this identity 11, we can basically go from the left to the right-handed representation of the Lorentz group, and one can also see that if one takes the left-handed spinor, the psi L, so the left-handed component, and forms this kind of strange objects, a complex conjugation and pre-multiplication by sigma 2, then this will transform in the right-handed representation. This will turn out quite important for our correspondence between matrix spinors and Dirac spinors. So still about the spin representation. So we have this fundamental identity 17, which relates the defining Lorentz defining representation of the Lorentz transformation. So the lambda mu nu matrix as it transforms the components of the space-time for vectors to the spin representation. One can write the corresponding transformation rule for the four vector. We define the v slash, that's the Feynman notation. We take the components of the four vector and use them as the coefficients of the linear combination of gamma matrices. So this is the v slash, and this object then transforms according to the right side of this equation 17. And from this transformation rule, so now I'm talking like the standard theory from basically, for instance, from Peskin-Schroeder. So how these spinors are discussed in standard quantum mechanics, quantum field theory. We can multiply this v slash with gamma 0, and then obtain an object which has our matrix representation of space-time vectors is v mu sigma mu as the lower component, the right lower component, and the v tilde, which is like analogous thing, but with the sigma bar matrices. And these have the transformation rules 19. So indeed, the v prime, so the matrix representation of four vectors, this is already what I announced on the first slide, transforms under Lorentz transformations via this conjugation with the right-handed spin representation matrix. So, and here is the correspondence between the Dirac spinors and what I call the matrix spinors, because I just don't have really any better name for that. Maybe, I don't know. So like you take a Dirac spinor, psi r components, and you just, from these four numbers, just rearrange them in the matrix, and you need to do it with some care on this right Coulomb of the matrix. This is because psi L transforms, looking at 21, transforms in the left-handed representation, psi r in the right-handed representation, and the matrix you want to end up with, you multiply it from the left with, say, right-handed representation. And so this means that both coulombs of this matrix will transform into the same representation. So you need to make sure that both of the coulombs of M transform in the same representation, and this is what you can do with this psi L complex conjugation times sigma 2. And there are some additional factors which turn out to be convenient when one, they are introduced for, let's say, later convenience. For example, if you think about the simplest possible matrix for the matrix spinor M, the identity matrix, you can see that this corresponds to psi L psi r given basically by this 1, 0. And this is a polarization spinor in the Dirac theory of a plane wave solution of the Dirac equation, with positive energy, which is at rest, and with spin up. So it's like the basic solution, the basic polarization spinor. And for us, it's the simplest matrix that we can think of. Now, notably, this correspondence 20, well, it's a one-to-one map, but it's not linear with respect to multiplication by complex scalars, because it involves this complex conjugation in the second column. So one has to be a bit careful, and when multiplying by I on the Dirac spinor side, this results in like kind of this operation on the side of the matrix spinors. So there is sigma 3, which is 1 minus 1, and this takes into account that multiplying by I, basically the I is conjugated here in the second column. Well, on the other hand, if one multiplies by I the M, then one gets gamma 5. So the gamma 5 matrix acting on the Dirac spinor, where gamma 5 in the Weyl representation is just minus 1, 1 on the diagonal. So again, it takes into account this this funny thing with the signs. If we write it, if we promote this to phases, we can see that the phase change of the Dirac spinor results in like a right multiplication of the matrix spinor by some exponential involving sigma 3. And on the other hand, if one just multiplies the matrix spinor by a phase, this amounts to a chiral transformation of the Dirac spinor. There are some other operations that one can think of. So let me show, for instance, if we just swap the columns of M, then in the psi picture, I would say on the Dirac spinors, this would correspond to this operation, charge conjugation of the Dirac spinor. So the charge conjugation is performed just with the swap of the columns of M. On the other hand, if we make a simple swap of the psi L and psi R component of the Dirac spinor, this is represented on matrix spinors by this with like a funny. Well, this is something we had already seen before, like this conjugation with sigma 2, which related the sigma mu and sigma mu bar Pauli matrices. Okay, now maybe let's spend a few words about Dirac bilinears. So these are quadratic expressions in psi, which are covariant under Lorentz transformation. So these are basically tensors, the space-time tensors that one can make out of Dirac spinors. So they are discussed in detail in the Dirac theory. And let's see how they get expressed in terms of the matrix spinors. So psi bar denotes the Dirac conjugation here, so Hermitian conjugation times gamma 0. And now, so there are several of these quadratic expressions. So for instance, the scalar, we just write it out in terms of the left and right hand components, we get this. It's a real quantity. The pseudoscalar is a purely imaginary quantity. And now, if we calculate the determinant of M, so the matrix M being defined here in equation 20, if we calculate the determinant, we in fact obtain a relatively simple expression in terms of psi L and psi R. And so this shows how the scalar and pseudoscalar, the Dirac bilinears, are related to M. Just those are the real and imaginary part of the determinant of M. I mean, imaginary part times the I. Also note the relation that if we multiply any gamma matrix on the Dirac spinor times gamma 0, then this translates to multiplication by sigma mu on the matrix spinor, and together with this 25, so gamma 0, we can then translate any multiplication by a chain of gamma matrices to some operation on M, which may be more or less involved. So before tackling the other Dirac bilinears, let's also realize that the scalar product, the Hermitian scalar product on spinors, it's written out like this. On the matrices, we can also quite naturally introduce a scalar product on basically always on the matrices. And the two are not the same. They are slightly different. It's a complex conjugation, but if we take the real parts of those, then they are the same. So we can use this observation to represent the vector bilinear or the Dirac current. What one gets is here that at the Dirac current, the psi bar gamma mu psi is just a mu component of a time-like vector j, where j is given by the matrix spinor as m dagger. So j is like the current in the 4 vector in the matrix representation, and we are just taking this component. For the pseudo vector, there is some extra gamma 5, and one gets this number to 33, so that we get the components of a spin vector, which is m times sigma 3 times m dagger. And with some more work, one can also express the tensor Dirac bilinear. Well, so I think this is enough for the Dirac theory, and now let's have a look at how these matrix spinors can be understood somehow more intuitively, more geometrically. So it turns out that they are just a matrix representation of even subalgebra of a real Clifford algebra of space-time. So let me just show some very basics of the real Clifford algebra or geometric algebra of space-time. So take a orthonormal basis of the Minkowski space-times E0, 1, 2, 3, and you can form a Clifford algebra over reals out of these, and this will have 16 independent elements, scalar vectors, bivectors, trivectors, and the pseudoscalar. And they have nice geometric interpretation, so they basically they algebraically represent like scalars are like some quantities, the vectors, arrows, and the bivectors are like 2 vectors taking and spanning some 2-dimensional plane. Trivectors are describing like 3-dimensional hyperplane, and the pseudoscalar basically is the kind of a volume of the whole of the space-time, the volume element of the space-time. So this geometric algebra is very nicely discussed in the book by Dugan and Lazenby. So it's what it is like for a mathematician. It's really a Clifford algebra over reals, but the book puts emphasis on like practical physical applications of these, yeah, which are quite nice. So if we consider the even subalgebra, so to say, that would be spanned by so-called even multivectors. So those are the elements that are formed by just an even number of the basis vectors. Yeah, So it's like this, so it's a scalar. Then the bivectors, where one can distinguish like spatial temporal bivectors, where one of the vectors is the time-like vector, and the other is spatial, or purely spatial vectors formed by two spatial vectors. And then we have the pseudoscalar as well. And this can be represented with 2 by 2 matrices. And the representation is quite straightforward. So the sigma I matrix, it represents the spatial temporal bivectors, which in turn are the generators of boosts. And the I times sigma I represents the spatial bivectors, generators of rotations, and I times the identity matrix is the pseudoscalar. And the identity matrix and the real multiples of it are is just the scalars. Yeah, so like just a quantity of something. Now, even if we have vectors in geometric algebra, we can just multiply them by any chosen vector. So let's take E0, the temporal vector, and we get to the even subalgebra. So from vectors we can form even elements, and there's a representation of vectors in the even subalgebra of the geometric algebra. And when one thinks about the matrix representation of this, then one gets exactly the representation of vectors as 2 by 2 matrices that that was the first thing that I defined in this talk. So really what we had seen, like
Yeah,
with
so,
the 2 by 2 matrices. Yeah.
Ask a question. Okay, so this is all in the context of mixed signature, Minkowski space.
Yeah, this is Minkowski space mixed signature for concreteness and for our purposes, like to discuss spinors in space-time. But geometric algebra can be done in any dimension, any signature.
Yes.
And it so very nicely generalizes. But this representation by 2 by 2 matrices is for the space-time and for the even subalgebra. We can use just the 2 by 2 matrices.
And you indicated the signature in the previous slide. You have 3 going to, yes, so E naught squared is +1, and the rest 1, 2, or 3, those are the spatial dimensions. So you're working in those being negative signature.
Yeah, this is the metric convention that is usual in quantum field theory, I would say.
Okay, and then so the even subalgebra of that Clifford algebra, or that geometric algebra, is going to be 8-dimensional.
Yes,
Have like the
indeed.
scalar is 1, and then the 4 choose 2 is 6. Choices for the bivectors, and then an additional scalar, pseudoscalar.
This is it. So we have 8 elements, and with the 2 by 2 complex matrix which is 8 parameters, you then represent any.
And right, and then so if there's and then the boosts are sort of bivectors where there's a component going in the E naught direction.
Yeah, there's the temporal component, and the rotations are just made out of the spatial vectors. So this
is there a Lorentzian transformation associated with the pseudoscalar at all? Or?
You can transform. I mean, yeah, you can transform like each vector individually, and then you can also transform any like chain of vectors. So you can transform the pseudoscalar as well. If you make a Lorentz transform, then the pseudoscalar will give again the pseudoscalar up to a sign. It depends whether the transformation is proper or improper Lorentz transformation. Yeah. So for parity, for instance, you would get a sign for the pseudoscalar.
I have another question. Like in general, for your geometric algebra, which is for like four-dimensional, right? So you have a general matrix representation as 4x4, and this is for the even subalgebra is 2x2.
Yeah.
So is it like just one block in the diagonal, or how they correspond to each other? Those two representations.
Yeah, so I think one could have a look here at the Weyl representation. For instance, you could have the 4x4 matrices to represent all the elements of the Clifford algebra.
Yeah.
And if you took like a product of the two, then you get the block diagonal matrix. So then if you restrict to
real, right? It's 4x4 real, not complex, right? You can represent because it's a real Clifford algebra, right? Not complex. Or is it?
Yeah, but the matrices can be complex, but you are only allowed to use real linear combinations.
Okay.
And this is what I have actually. So the even subalgebra consists of 8 elements, and the real Clifford algebra combines them with real parameters, but they are represented by complex matrices.
Yeah.
Which is a bit, but it works out quite nicely.
Mm-hmm.
So if you take, for instance, you can take the complex matrix and multiply by a complex number, but then the I in the complex number geometrically is a pseudoscalar. Yeah, so this would amount to multiplication, some scalar plus a pseudoscalar. It's an operation which also you can do on the abstract level in the geometric algebra.
Yeah, I know that practically you can use the usual complex component, I, not the pseudoscalar, just to go from like Clifford algebra 3-1 to 2-2, any Clifford algebra that is 4-dimensional but has different squares, like -1 and 1, right? You can use I to just transform between them.
Yeah, then you have to like distinguish whether your I is really like a geometric, whether it's the pseudoscalar or whether it's just like the I of the scalars that you are using to the field over which you are making your vector space in geometric algebra.
Yeah.
So like then in principle you would have like 2 different complex units, maybe I and J, and the I would be for the pseudoscalar and the J would be for like the scalars, which would be complex, but that would that wouldn't make things more easy or more transparent, but sometimes it can, I guess, be handy maybe, but not necessary here.
Yeah. Okay. Thanks.
So here everything really is like visual, clear, and so in geometric algebra there is a standard way of talking about spinors, and the spinors for the people in geometric algebra are indeed even elements of the geometric algebra of space-time at least, and space as well, and so these.
By the way, I also heard that they called like ideals, not just even elements, but ideal, left ideals or something like that. Is it important?
I have read this several times, and yeah, it became too algebraic for me. So I'm more geometrically minded. I just see this and I'm done. Like with the ideals, I'd have to recall it. It is the way they talk about spinors often. Maybe this is a fancy way to saying the same, but I'm not sure. For me, the spinors are the even element. That's it.
Yeah, that's fine. Maybe it's not really important, but the fact that it's element of even subalgebra is just.
Yeah, but indeed, like in the literature, one sees this like many like ideals, but maybe for someone more algebraically minded, it would be more accessible. Well, there is a standard way to think about spinors, as I said, as even multivectors, and the standard correspondence between spinors like Pauli or Dirac spinors from the quantum theory and those even multivectors. And of course, it turns out that this correspondence exactly will yield our matrix spinors once we matrix represent the even multivectors. So we already made this matrix representation of the even multivectors, and now just to make sure that the two approaches to Dirac spinors are compatible. So let me recall, for instance, in Doran-Lazenby, this representation of Pauli spinors, so two-component complex vectors in the geometric algebra, and I'm already going to the matrix representation of the geometric algebra, but 39 is basically what they give, how to represent any Pauli spinor by so how to represent it in the even subalgebra. And for the Dirac spinors, those are like basically two Pauli spinors stacked on top of each other, and they give this relation 40, but they work in the Dirac representation, Starland representation of gamma matrices. And now just if we translate it to the Weyl representation of gamma matrices, the wave functions are related like this, and what we get from 40 is exactly the matrix spinor, or what I call matrix spinor, from the definition 20. So in this sense, it's compatible, everything is intact with the approach of geometric algebra. So we are doing really nothing fancy. We are just using a matrix representation of the even subalgebra of the space-time geometric algebra. So it's nothing fancy, but I would say it's a convenient middle ground between Dirac spinors, like very concrete four complex numbers, and the even multivectors, because it can be sometimes maybe hard for people who come from the Dirac spinors to like appreciate this geometry of geometric algebra. But this 2x2 matrices, like they are kind of in between, so they make it easier maybe for one to translate from one realm to another. But so we have still like a couple of more slides, so some more observations for a generic matrix spinor. So we can write it as a linear combination of sigma mu with complex coefficients. So this is a generic 2x2 matrix. And now in geometric algebra, we can, with any even element, we can make this conjugation by the time-like vector and stay in the even subalgebra. And this is with parity transformation. So on the level of matrices, this corresponds to this sigma mu and star sigma mu. And it's a transformation that flips the sign of the pseudoscalar and of the spatial temporal bivectors. This parity transformation, so it flips the sign of each spatial vector, and this is the result. And here we have the way how to write it in terms of this 2x2 matrix. For the so-called reversion in geometric algebra, we have n tilde, which is this parity followed by Hermitian conjugation, and again it flips the sign somehow. It flips the sign of signs of all bivectors, in fact, in this decomposition of the spinor. And the Hermitian conjugation on its own just makes this sign change, in the spatial bivector in the pseudoscalar. Okay, so just to mention another thing would be also this nice relation for 46 that m times m reversed, which is just z mu, and in turn this is just the determinant of m. So this basically makes it transparent how to take an inverse of the matrix spinor, for instance. Yeah, so this inverse would be just the m tilde divided by determinant of m. Can be handy sometimes. If we take the polar decomposition that we discussed earlier, so the generic matrix spinor, generic 2x2 matrix, decomposed into Hermitian times a unitary matrix, we refine it a little bit so that we take the determinants of this Hermitian and unitary matrix out, and have this H0 and U0, which are then of determinant 1. So they represent, so they are basically spin representation of boosts and rotations, respectively. Then we can cast this polar decomposition in the form which is standard in geometrical algebra. So it writes a spinor as essentially as R, which is a Lorentz transformation times some magnitude and phase. So the spinors in geometrical algebra in this decomposition are understood as instructions for Lorentz transformation times some magnitude and phase.
It's a rotor, right?
It's a rotor, this R, yeah. That would be called the rotor in geometrical algebra. But it's on the with the 2x2 representation, it's just the element of the SR lambda. So it's some spin representation, right-handed spin representation of some Lorentz transformation. Well, and maybe kind of a moral of this approach to spinors that indeed, like psi and m are equivalent. We had this boxed equation that translates between the two, but some operations are quite natural on the level of matrices, and they get quite nasty on the level of Dirac spinors. So for instance, if you take the Hermitian conjugation of a matrix, then this is given by this kind of complicated expression on the level of Dirac spinors, which involves some complex conjugation and some reshufflement of the components of the Dirac spinor. If you take an inverse, which is often quite handy to have, and when you calculate, when you manipulate equations to have inverse for your objects, so this is even more complicated, or at least this is what comes out when you just kind of directly apply the rules how reversion is represented in terms of the spinors and the determinant m, how it's represented in terms of Dirac spinors. I don't know if this can be simplified in any way, but those operations on the right would be very hard maybe to envisage for Dirac spinors. Not sure, maybe someone uses them, but at least they are not standard. But on the level of matrices, this is like the first thing you would do with the matrix. So maybe writing things in this matrix representation from spinors would open like some new horizons, or some, well, maybe horizon is too much to say, but some new ideas to how to deal with spinors. Last thing that we kind of discuss spinors like at one single point, but we can take functions. We can take this translation between psi and m at every point of space-time, and then, for instance, rewrite the Dirac equation in kind of a geometrical algebra or S10S form. So in the geometrical algebra, it is known that the Dirac equation for psi's as even multivectors can be written like this, 51. And if we just go to the matrix representation, then we get 52. And so this is an alternative rewriting of the Dirac equation. And Stanesh himself studied this on the level of geometric algebra, quite extensively. So trying to give some geometric interpretation of the Dirac equation, basically. So to conclude, maybe to just summarize in a nutshell what we have seen today. So we took a 4-vector, represented it as a 2x2 matrix Hermitian, and took a square root. And this square root is a spinor. So this is, for me, this is just super direct way to spinors. And we showed how this corresponds to the Dirac spinors that one knows from quantum field theory textbooks. We showed that those matrix spinors are just geometrical, are just a matrix representation of the geometric algebra, which has like nice geometric interpretation. And I would say this emphasizes for me the fact that spinors are not inherently quantum; they are really just geometric objects, and then that one would perhaps look for more applications also in quantum physics. No, I mean in classical physics. I mean, of course, the spinors are discussed in quantum physics, like they are like kind of necessity to write the quantum physics. In classical physics, perhaps they are not necessary, but still, like they have some nice geometric properties, and they might simplify some things which already has Stanesh pointed out, or maybe other people. And I would end up with a popular quote by Michael Atiyah that no one fully understands spinors, and in some sense they describe the square root of a geometry. So this sounds quite mysterious, but it's like it resonated in my head, kind of. And what we have seen today, taking the square root of v to get the spinor, it's like the actual like implementation of this square root idea, like in like algebraic terms. So thank you for coming and for your attention.
Yeah, thank you so much, Vaclav. That was quite a pedagogical guide through this topic. And just to add to your quote here, this is not only a quote, but I can attest personally, when I was working with Michael Atiyah, I mean, I was, just for reference, I was his research assistant for how much, maybe 2.5 years before he died, just at the end of his life. And when I met him in a talk about spinors that he gave in Edinburgh, at the end of the talk, he comes to me and says, "You know, Carlos, I've been thinking about this for about 50 years now, and I think I'm starting to understand spinors now." Like, this was Michael Atiyah at whatever, how old was at the time. Just told me, I think I'm starting to understand spinors a little bit. So yeah, I think this is I love the spirit of the content of your talk. This idea that spinors are not inherently quantum, that we should be thinking of geometry. And I think what is that? Geometric algebra does a good job at showing that this notion of complex like phenomena, I mean complex as in complex numbers, is something that need not relate to something to traditionally complex formulated theories like quantum mechanics or something like that. And I think it's interesting to consider. I think if you look at geometry, and so 3D geometry and real Euclidean geometry or metric geometry, let's say, and you scrutinize it, you realize that complex numbers are a way, at least in some interpretation, kind of are a way to describe rotations, and of course the fact that you have sort of oscillatory phenomena and anything that has to do with oscillatory phenomena be so tightly packaged in complex number notation and complex number formalism, right? I think that, in my opinion, that is kind of like the first step, that you go into this domain where you happen to have something like a number field behavior, which is the complex numbers, but you actually are encoding a geometric notion, which is rotations, right, or axis rotations or whatever. And to me, geometric algebra has always been, I mean, I'm not an expert on it, but it's always been this promise that let's take that lesson and let's try to take it as far as we can, right? Like, let's try and you know, not stop at what happens when you do kind of real dimension 2 kind of sort of instance, but really try to generalize as much as possible this sort of philosophy. And you know, there's nothing quantum about that. It's just, you're just thinking of you're kind of taking a maybe more algebraized or more I don't know, compact or more tidy approach to just 3D geometry and 3D operations or metric operations in general. So yeah, I think that's always been the promise for me. So it's always cool to see these applications, in this particular case with spacetime, so 4-dimensional spacetime and Dirac spinors and so on. It to me, it kind of compounds on the same theme, and definitely also furthers in the direction of what Atilla was mentioning about, you know, us not fully understanding spinors. But yeah, so great stuff. Any questions, any comments? We have some time to chat now if you have some time to stay.
Well, maybe we should explore this physical interpretation, especially this rotor thing, and how this everything you know corresponds to physical rotations in space-time, whereas it doesn't require imaginary component and it's all real in a sense, and the nature of the Dirac equation. I don't know. It's just this kind of thing we can talk about it.
Yeah, I think one slide for what you just said, Nick, that caught my attention was, I can't remember the number, but there was the where you have the different rotations, the different transformations that correspond to each of the matrix spinors. I think it was in the first half for sure.
This one?
No, I don't think so. I think it was earlier than this.
There's not much more.
Oh,
No, but do you think this Hermitian conjugation, reversion, this was the transformations here? Oh, conjugations.
what am I thinking about?
Um,
No, it was when maybe the one that you said corresponded to boosts or rotations or.
I would say this slide, maybe.
Oh
because
yeah.
we have the
Sorry, yeah,
bivectors and
I was looking at the wrong part of the slide. Yes, sorry, yes. Yeah.
Mhm.
I think this is what you meant, Nick, right?
Well, partially, yeah.
Yeah.
But also like all kinds of rotors that you just build from these objects, right? With maybe some exponential map. And
yeah.
what's the actual meaning of that? Right?
Well, I
Maybe-
think it's basically Lie algebra, Lie group correspondence. So you take an exponential, and these like bivectors. They are your Lie algebra, and if you take an exponential, you get like to Lie group.
So what I remember we had a conversation about this years ago, Vaclav, in one of our retreats where we met. But what is the Lie algebra that you get in bivectors?
So the bivectors are your elements, and you take the commutator product. So you really take a commutator of of two bivectors, and you get the bivector again, and so it encloses in as an algebra. So the product is the commutator.
Right. But what I mean is, so say we are in, I mean, okay.
Yeah, but it's algebra SOPQ or SO13 in this case. So.
Oh, really?
Yeah, just the algebra of rotations and or Lorentz transformations in space-time. So Lorentz algebra. This you have really sigma I and I sigma I, and you can take the real linear combinations of those. You have 6 parameters, and so it's nothing like esoteric. I mean, it's
of course.
It's a bit like more abstract way of talking about exponentials of sigma matrices. And here I'm using like the explicit representation by 2 matrices. So if you do it, the Clifford algebra, the geometric algebra in space-time, you kind of have this representation with matrices, which is quite compact, and then you get the standard things from quantum theory.
Well, I mean, something that's interesting is that what I find kind of interesting about this is you get, if you define your geometric algebra, so let me put it this way. If you want to get to the Lie algebra, let's simplify and let's think of Euclidean theory space, just for concreteness, right? But it shouldn't change anything for the sake of argument. So if you want to get to SO3, little SO3, so the Lie algebra of rotation, so just the cross product algebra, right? In 3D, unless you know how to get there and define your whatever, your determinant with the volume form or whatever, you're going to have to take rotations as isometries, and you're going to have to compute your Lie algebra out of it, right? You're going to have to, in order to conclude that your algebra is SO3, you will have to compute infinitesimal rotations and actually derive the commutation relations from your basis elements if you want, right? So what I find interesting about this approach is that you can somehow shortcut getting there. So if you know that you should be defining this geometric algebra, and you have the intuition that bivectors are going to induce some kind of transformations, then the Lie algebra just shows up in the bivector subalgebra of the geometric algebra, right?
Yeah, so like or in geometric algebra terms, you form a rotor, and you know that this rotor will rotate, will do the rotation, and then you can take a look how to form a rotor, and you realize that taking an exponential of a bivector will do the job.
Yeah, what I find fascinating is that we don't typically think of rotations as bivectors, and I think that's what is, to me, this is the most novel aspect of geometric algebra. So is the right intuition that the bivector, in the case of 3D rotations, is the case that the bivector is the orthogonal plane to the axis of rotation?
Yeah, that's the plane in which you rotate.
Right. So I guess you're taking sort of XY bivector is the XY plane and so on, right? Like in order to, right. So that's what I mean. Like that to me is a clear advantage over the typical approach. Like you don't get to kind of, it's going to be very graphic, but like to touch the Lie algebra of rotations, you have to either know that this quote unquote magic formula of the determinant of components works out, and you know that you should be multiplying things in this funny way, or you compute it explicitly with rotations. You define rotations; those are easy to define because they are just isometries, and you compute the infinitesimal ones, and you get a Lie algebra. So, in some sense, there's no easy approach to that. But with this approach, it seems to me that once you have the algebra set up, then the Lie algebra just springs out of it. And what interests me is that this is nothing specific to rotations. Every time you have a metric, you're going to have this algebra, and you will always find your Lie algebra in this way.
Yeah, I think this is what Hestenesh emphasizes too, like that.
Right.
Like,
So then, sorry, Nick or Dugan or James, did you have any other questions? Because I have a follow-up on this.
No, definitely no. Please do your follow-up.
I think Nick might suspect where my follow-up is going. So what happens when you take like 3 blades, right? This 3, for example, like what kind of like what happens? What happens there? Like in the 2 blades you get the algebra, in the 3 blades, what do you get?
I don't seem to get anything interesting. So with the 2 blades, you get generators of rotations, so to say, these 2 blades. If you consider trivectors, I haven't seen like any like really application that would be somehow persuasive that they have like some interpretation when you exponentiate them. Yeah, it doesn't seem to give anything.
This now really kind of entices me because this seems like a promising thing to find my favorite animals, these ternary algebras, because you know, in 4D, right? The reason what I'm saying is that, in fact, it might be a good exercise to try to figure this out live with you here, because Vaclav is very fluent in geometric algebra, as I imagine our audience will be figuring out at this point. So okay, so how do you? I'm gonna tell you a construction that I think you probably heard from me at some point in the past, but I'll just say very briefly, and you can tell me, okay, that's how I would understand this in geometric algebra. So I go to a metric vector space, and I go to so it's n-dimensional, right? And finite dimensional dimension n metric vector space, and I decide to construct the following application, the following mapping. I'm going to take n-1 vectors, and I'm going to try and build another vector out of these, right? So the way I do it is I say, check if they are linearly independent. If they are, then you have a non-zero vector. If they are not, you have the 0 vector. That's the first check. And then if they are not linearly independent, what you do is you fill them into the volume form, that, you know, induced volume form from the metric of the vector space, and you get, there is a unique positively oriented orthogonal vector to all those vectors, right? So that one vector, that's the output of the operation, right? So that construction gives you, in dimension 2, in positive signatures, in dimension 2, it gives you the complex structure of complex numbers. That gives you a 2 minus 1 array operation. So that's a unary operation. So it's just multiplication by I in the complex plane. In n equals 3, that gives you a 3 minus 1 array, so binary operation, which is the cross product when your signature is positive. And in 3 dimensions, it gives you a ternary product that happens to be what people call a Filipov algebra, so a ternary Lie algebra. So it satisfies the ternary Jacobi identity. Basically, what you get if you would take the derivative of a triple product in just usual calculus, right? Derivative of ABC, you get, you know, derivative in each of the arguments. So the bracket behaves like that kind of derivation. So you take the triple bracket of something, and then that something gets into 3, and then distributes in that way, like the Jacobi identity way. So perhaps, I don't know, hypothesis, the 3 blades form such a Lie algebra. So before we go there, how do you understand that construction in terms of geometric algebra? Like, because that to me seems like a super standard thing to do. It's like codimension 1 positively oriented complement, right?
Yeah, so you take 3 vectors, you take a vector product of those.
Yes.
And then you put the pseudoscalar at the end. So this is like the thing that maps from the 3-dimensional plane to the 1-dimensional vector, in the case of 4 ambient dimensions.
Yes.
So you can, yeah, okay, you can write this quite nicely. I would have to see like what do you more in detail what do you mean by this ternary algebra. So say you have vector a1, ab, a1, a2, a3. You wedge them and put the pseudoscalar, and then you have another trivector b1, b2, b3 times I. And so, like, what do you do with these two trivectors? What is the operation?
So no. So you get an operation. So for the construction that oh right. So you're saying in the case where so the idea would be that we are looking for a ternary operation on trivectors, right? So
take three trivectors and do something.
three trivectors. So maybe we can try and guess what would be like the choice. So the game is that you want to get from three trivectors, you want to get another trivector back.
Okay.
Which is in the same way. And I think the exercise should be take inspiration to what happens in the commutator case of bivectors, right? But I mean, it's not obvious that you're going to take the commutator of bivectors and you're going to get a bivector, right? Like, there is some cancellations going on, right? So maybe that's...
I mean, with the three trivectors, it's like quite natural what to do. So you can, each of these trivectors, you dualize to get the vector, and then you wedge the three vectors, and you get a trivector again.
But this is in the four-dimensional case.
In the four-dimensional case.
No, but the point is, so
in the two-dimensional case, yeah.
Yeah. The point is, I mentioned that the construction I refer to, which I think is exactly what you said in geometric algebra. What you do is you wedge three vectors, and then you wedge the pseudoscalar at the end. So that gives you a one vector, right?
Yeah.
So
I think that this would work also maybe for the in dimension 3 and for the bivector. So if you take two bivectors, each of them you dualize and then take the wedge, that it should give the commutator of the two bivectors in effect. But
right.
I think that should hold, but I would have to work it out maybe.
Right. So exactly. So the point is, because the commutator of bivectors is dimension independent, right? You always get the algebra defined by the commutator of bivectors, regardless of the dimension. My point here is there might be a construction with, and I'm saying three trivectors just because I'm expecting it to be something like a ternary. Maybe it isn't. I don't know, but there might be some construction with trivectors that that allows you to somehow combine them and get back a trivector in any dimension, right? And if you do it in dimension 4, then you would get this construction back where you're dualizing and taking the wedge, like you do with a binary case in 3 dimensions. So that would be like a reality check that if we have a kind of a candidate for such a construction, we could test it in the 4-dimensional case to see if it matches. But anyway, I think that would be an interesting thing to think about, because if actually, so if that would work, what you would be doing effectively is defining the ternary commutator of trivectors, right? In the same way that bivectors, you use the ordinary commutator, right? You just do AB minus BA, effectively. A wedge B minus B wedge A, right? Not wedge, but geometric algebra product, right?
For the commutator, it's the geometric algebra product in one way and then in minus.
Exactly. So that's so here you would be doing geometric product ABC for trivectors ABC, and then some permutations of these with some weights, right? And that's kind of an open thing on what to do. And actually, a few live streams ago here, we talked about this in a kind of related context, actually, Nick, right? Like we were talking about 2x2 complex matrices as well. It was like this thing is kind of like orbiting a similar conceptual dimension. Like we are not going too far from.
I could have asked a bunch of questions about like qubits at the beginning, but I didn't. Like, because
maybe, yeah.
it's like it was essentially like deriving like some kind of block vector when you do your vector 4 vector is like a block vector with the additional identity thing.
And maybe this is a good time to ask those questions. So go ahead.
No, it's just well, if you can, if you go to the beginning, just it's not really a question. It's just about like a relationship. Like here, this 4 vector and the projections with the Pauli matrix is just like if you ignore the sigma 0, you get a block vector, right? So essentially, this is just a representation. It's like just a density matrix,
Yeah.
right? Versus a block vector, but in 4D. And when I see this combination, when you use all of those 4 Pauli matrices, this matrix representation is just a way for me to represent a qubit in phase space. So that's kind of the relationship. I usually ignore the matrix structure, thinking of it as 2 by 2, but I also usually flatten this, right? So it's instead of 2 by 2 matrix, I just flatten it to 4 vector, but with those components, right? And do some other linear transformation on those. And this is just different representations of the qubit in the phase space.
What is the qubit in the phase space?
Well, qubit in the phase space is, well, you're essentially looking at it. It's just this 2 by 2 matrix by flattened, but flattened into 4 vector, right? But you can also linearly transform it and have a much more realistic representation of those numbers. You can think of them as quasi-probabilities or probabilities. So that's what it is. That's why it's phase space.
Yeah, I would have to like see it. Maybe the definitions. I mean, I understand what you say, but what the relevance and stuff like that would have to be worked through, I guess.
Yeah. Yeah, we could schedule some life science sessions where it's not so much a talk, but we can, because I feel like, so a few weeks ago, Nick was presenting this idea of showing sort of qubits in the phase space and kind of representations embedded in 3D and 4D and projections and all these kind of geometric aspects of qubits. And then unrelatedly, I've been thinking about these ideas of ternary commutators. And the funny thing is that people don't know how to do ternary commutators. I mean, people would say, oh, we just antisymmetrize a trilinear form or something. Everyone knows how to do that. But the honest generalization of a commutator would be something that takes S3, the group of 3-element permutations, and somehow represents it fully in your sort of field of numbers. And so things stop being commutative and things are kind of get complicated. So it's much more bizarre than usual just symmetrization. So I suspect that's not what's going to happen in this geometric algebra business. If there is something there, I imagine that would be simpler. It might just be pure antisymmetrization because these things are all skew symmetric in this sense. But still, there is something going on around this topics of sort of like spin representations, qubit phase spaces, and like all this geometric algebra interpretation that gives you kind of a more direct algebraic handle on things. So it might make sense to just, in a few weeks or something, we can schedule a life science session, which just work on this question, and we kind of present our understanding of these things, because it's kind of a cool thing that there are some questions that they seem like undergraduate level simple. They really seem like this is what people learn when they are doing their homework in quantum mechanics or something, or in whatever, Lie theory, when they are learning B groups for the first time in physics or something. But I mean, when you dig down a little bit, you realize that there's something non-trivial and there's something that people don't really understand. And there are open questions that can be formulated, and we could maybe try and answer. And yeah, anyway, just a suggestion, because I do have to go in 5 minutes to another meeting, but it was great to have this presentation. I think it was very cool.
Yeah, so maybe if there is something about this phase qubit to look at, I would be happy to look
Yeah.
and think.
Yeah, I'm also curious why these 4 vectors, how they correspond both as space-time 4 vector and a probability vector somehow are the same.
Mhm.
Can be thought of the same thing.
Yeah, there's definitely some connections here. So yeah, this is exactly just for the record for our audience and for everyone following. This is exactly why we do these seminars. We want to find this kind of deeper connections that are not obvious than when you just look things superficially or on your own, and then suddenly start to communicate. You see patterns, and this is how research goes, right? Like research is not like when you're doing homework in your degree that you have kind of the expected result and you're working towards it. Like you start to see kind of like patterns or glimpses of things. Oh, right, maybe a connection here, and slowly we're kind of unveiling that, right? So it's that's part of the sort of exciting adventure of research, and that's what we're trying to do. So yeah, Vaclav, thanks a lot for your presentation. I think that was very clear and very much suggestive of further connections. So that's always appreciated.
Okay, thank you for having me.
Yeah,
For
pleasure.
presenting, and thank you everyone for tuning in.
Right,
We'll
everyone.
see you again next time.